I will remind some of the things which we discussed. Yes, suppose K as an attractor is the attractor of a system S1 Sm, therefore we have M maps and M copies, yes, and let gamma be its its intersection graph. So suppose we have self-similar set K and we consider its intersection graph. For example, let it be a von Koch curve, for example, yes? So, can you construct the intersection graph of this self-similar set? Supposing that it is generated by 1, 2, 3, 4 maps. So, let us produce this. So, we have K1, this will be K1, this will be K2, this will be K3, and it will be K4. There are 4 copies. Yes? And they have 1 point, these copies have 1 point intersection, these copies have 1 point intersection, and these copies also have 1 point intersection, so this graph will be a line. Yes. And if we take Sierpinski gasket, here it is. So it's what will be the intersection graph of this set? We'll have K1, K2, K3, K2, K3, and there will be edges between these copies. I also need to remind you one fact which I proved yesterday before we shifted to the construction of examples using IFS style. I proved that the set how it is denoted VRK of X, V rho K of X, which is the union of KI1 IN such that diameter of KI1 IN less than rho and less or equal than rho and K and the sets were okay and less than K I1 IN minus 1, yes. So I mean that we take a point and consider copies containing this point. Yes, but these copies whose diameter is less than rho, and previous ones are greater than rho. Yes, so these sets form, if you take rho n forming a sequence converging to 0, so the sets V rho n of k of x form a fundamental system of neighborhood system of neighborhoods of x in K. So this is just a technical moment, but we will use it very soon. So if, for example, if I take this point here, right, then this V rho n will be unions of triangles. Yes, I take this one and this one, they form V rho, I say 1/4, and this one and this one will make V rho 1. So if this is 1/2, this 1/4, 1/8, and this one and this one form V rho of 1/16, etc. Yes. So this is a good fact. And we will use it very soon. This was the first. So I'm interested when the self-similar set is connected and when it is disconnected. So there was very old, well-known result. If the sum of all contraction, so let Q1, Qm will be contraction ratios of Si. Si. Yes. So suppose we have these contraction ratios. So in this case, all the contraction ratios will be 1/2, right? This contraction ratio is 1/2. This contraction ratio is 1/2, and this is 1/2. Yes. If the sum of Qi from 1 to m is less than 1, then K is totally disconnected. This is a very simple statement, and it follows on such a consideration. So suppose that K is not totally disconnected, and we have some points x and y lying in some connected component of K. Yes? So we can consider that they are connected by some kind of continuum, yes? Yes. And if these points are connected, then dimension of this set is not less than 1. Because if a set is connected, the dimension is greater or less than 1. Yes? Yes. But if you consider a path, so we have a sequence of copies connecting x and y. But if the sum of qi is less than 1, then I will show it that the dimension of k is also less than 1. And it will be done a little further. Yes. And third statement was the following. Three. If the intersection graph of K is connected, then K is connected. It is arcwise connected. And locally connected. This result was proved by Masayoshi Hata in 1985, his 1985 work. And also this result is explained in Kigami's book, Analysis on Fractals, Jun Kigami's books. Yes, and it also appears in many other places. So I will not plunge into details, but explain what is the principle, what is the idea of proof of this statement. So suppose that the intersection graph of K is connected. Yes. Suppose the intersection graph of K is connected. Then, so we take 2 points in K. For example, x and y. So x lies in some one copy, say K1, and y lies in some other copy. And since the intersection graph is connected, there is a path, yes, from this copy to that copy, which goes through the intersections of this copy. So we have such a situation. So we have some K1, and we have X, then K, maybe Ki1. And then we have Ki2, and then we have some Ki3, I3, and then we have KIN. So we have a sequence of copies. First copy contains X, and second copy contains Y. Okay. If this copy pairwise have non-empty intersection, then we can find the points, choose some points in these intersections. Yes? Therefore, we have a kind of path, but this path is not continuous, yes? So this is a path, discrete path, and the distance between the copies is less than rho k. Rho multiplied by diameter of k. Diameter of k, right? Okay. Can we make this path? So this path is just a sequence of of points, and the distance between two subsequent points in this sequence is less than rho multiplied by diameter of k. Can we make it find a more dense sequence of points with pairwise distance between them, so that this distance would be less than, for example, rho squared. Oh, sorry, not qk, q, yes, q. We have so q is maximum of qi. Yes, qk, yes. So it will be q less than q squared of k. How to do this? So consider this copy, yes? And we have some of these copies, and consider the points. It will be xi and xi plus 1. I plus 1 in this intersection. So we can take the preimage of this copy and preimages of this si minus first minus 1 of xi and si minus 1 of xi plus 1. Now we are again in the initial attractor, and these 2 points, since the intersection graph is connected, can be also connected by a change of pairwise intersecting copies. Yes, such that first of them contains this point, and the first contains this point, and the last contains this one. And we take the intermediate points in intersection of this copy. So we came this way, we get a ramification of this sequence, yes, and pairwise distances between points will be less than q squared by diameter k, right? Then repeating these steps, we will finally get a path in k. As a limit, we get a path in k which connects the points x and y. Therefore, we see that k is any 2 points in k can be connected by a continuous path. So k is arcwise connected. Since K's are arcwise connected, it's connected too. Yes. But now we look at this statement and take any point in K and consider neighborhood V rho K of X. This neighborhood is a finite union of images of K. Yes, which have one common point. So we have X and we have several copies which form a raw neighborhood of X in K. These copies are connected, and if we have union of several connected sets having one common point, this union will be connected too, right? I don't see your reaction. Is that right? If we have several connected sets having common point, this union will be connected. Yes? I will be pleased very much if anyone disagrees. And then I will be obliged to prove this, but the proof is very simple. So each point has a fundamental system of connected neighborhoods, which means that K is locally connected. So yes, this is very interesting. There are two sides of these questions. First, are there disconnected but locally connected self-similar sets? Can we construct a self-similar set which consists of several components, for example, from two components? Yes? These components are connected and locally connected, but they don't intersect, of course. Oh, this example is easy to construct. I don't know, maybe I will erase this first line to show it. It will be 1, this will be 2, 0, 1, 2, 3, 4, maybe it's enough. And I consider, yes, 1, 2, yes, 1, 2, and 1, 2, this way. So I want to draw a picture, but it's a problem how to draw it. So I draw one copy. It looks this way. One. Second copy. I don't know why these markers are all black. Can anybody provide me different colors? Is it possible to fetch red or green one? Yes. Okay, but this time I will do this. Second copy will be drawn by this line. Yes. So it will be 0, 1, 2, 3, 4. Now I have a gap 5, 6, 7, 8, okay, and 9, 10, 11, 12. And the second copy will be this way. Oh, no, sorry. This, and so it will be K1, this will be K2, this will be K3, and this will be K4. Can you draw this picture? Is this a self-similar set? So you see, K1 is K divided by 4, right? Oh, so I'm indebted to you for all my life. Thank you. Yes, okay, K1. K1 is, so we have 1/4 multiplied by K, right? We have a contraction of K in 4 times, yes? K2 is 1/4, so 1/4 multiplied by K, and it is shifted by 1, right? It is shifted by 1. K3 is shifted by 8. 8 plus 1/4 multiplied by K, and K4 is shifted by 9. So we have a self-similar set which consists of 2 connected components, yes, but these components are straight line intervals, right? So it is disconnected, but the components are good, they are locally connected. So this is one example. So if the attractor is locally connected and contains finite number of components, then intersection graph is disconnected, but all other things are good. And now I want to provide you an example when a self-similar set contains uncountably many connected components, but these connected components are lines, yes, and it is not locally connected at any of its points. Do you know the simplest example of non-locally connected self-similar set? Can you provide me the simplest example of non-locally connected self-similar set? Fantastic. You fill my heart with enthusiasm. Cantor set. So, if you take a square, 3 by 3, yes, and make copies K1, K2, K3, K4, K5, K6, right? K6, sorry. You see? So this will be a fractal square. So it is generated by 1 divided by third homotopy, yes, and also translations to these points. 0, 0, for example, 1/3 0, 2/3 zeros, etc. Yes? If you look at the attractor of this system, we'll see that this attractor is a product of counter set and vertical unit interval. Do you see? Yes. I see that you don't believe me, and I need to prove it by experiment. One second. Let me put it here. I will write L equal to, so we have 6, 6, so we have 1/3, 1/3. Do you see what I write? Yes, it is visible. So I took a program. I don't care too much about this program. I just write one line, and it will be enough for me to make a needed object, and if necessary I will erase it. So I take 1/3. So this is a homotopy, and then I multiply it by the union of shifts. So 0, 0, 1, 0, 2, 0, 2, 0, 2, 1, 2, 2, 2. So let us, I don't want to write 6 operator because I can write only 5 of them. So I make it this way. I take first I take 0, 0, union 0, 1, 0, 1. So I have a wrong, yes, of course. Please change the order of coordinates. I 0, 1, and union 0, 2, 0, 2, 2. So this will give us a vertical line, yes, and I multiply it by a counter set. Counter set will be 0, 0 again. To write 0, 0 is very difficult job. I will just write 1 because 0 translation is identity. It was not wise of me to write 0, 0 here too. I write 1, yes? So I economized the electronic ink, and here it will be 2, 0. 2, 0. 2, 0 is the optimal way of. And all this will be multiplied by this set L. Okay? That's all. So this string is completely independent of others, and it will be also evaluated and shown on the screen under our request. So I apply this. Okay. And let us consider, here you see there is L in the list of possible objects. There are T, K1, K2, K3, and L. Do you see it? This is L. It's a product of counter set and vertical line. I don't know why it... So, if I magnify it at any extent, we'll have the same picture, right? Yes. So, any of the point here has a neighborhood which contains of uncountable disconnected union of vertical lines. Yes. So it is not locally connected. Yes. Neither of its points has a system of connected neighborhoods. So let us proceed further. Let me check. When we need to finish? 10:30. Okay, so we will finish at 10:25. This will be my gift to you. Because the breaks are too short. You cannot recover during such breaks. And me too. One second. Let me look at my plan. Yes. But truly, next topic will be about dimension, because our tale of connectedness came to an end. So we can make a break, and then maybe begin a little earlier. So what is it's 10:30, 10:45. Can we begin at 10:40? Okay. So please relax. Meantime, you can ask me questions.
There is a tea break now.
What?
There is a tea break of 15 minutes, as we have a schedule in our...
Please.
As it is scheduled, there is a 15-minute break.